What's up, guys? Welcome to my class. And today we're going to talk about the equation of motion in a central force field. First, let's recall the concept of angular momentum. Angular momentum is described as the cross product between the position vector and the momentum vector. Okay? So, for example, we have a particle of mass m uh, defined by the position vector r, and let's say this mass has momentum p, which is defined by linear momentum p, which is defined by the product of the mass of your particle and to the linear velocity of your particle. Okay, so the angular momentum is position cross linear momentum, or that's also equal to r cross mv. Okay, so several things that we need to know here is that number one, L is normal to the plane created by R and P, or R and V. So for example, this is the R and this is P. So the plane created by R and P, whatever the line that is normal to that plane, that is where your angular momentum will be pointing at. Since this is a cross product, the magnitude of the angular momentum is equal to rp sine theta, where theta is the angle between r and p. R is the magnitude of r, so that means that the distance between the mass of your particle to some reference point, and then p is the linear magnitude of the linear momentum of your particle, and that is equal to mvr sine theta, where m is the mass of your particle, v is the speed of your particle, and r and theta has been described earlier. Now, we all know that the plane created by r and p has two perpendicular directions, one in this direction and the other in this direction. Because this is the cross product, the direction of our cross product will follow the usual right hand rule. Okay, so that means the order of your cross product, r cross p, will be the opposite direction as when you take the product between take the vector product p cross r. Okay, so following the right hand rule, if for example in this illustration this is r and this is p, the direction of your L is in this direction. Okay, easy. Now, let's get the time derivative of your angular momentum. Time derivative of your angular momentum. So, taking the time derivative of your angular momentum, okay, and applying the definition here, this is derivative respect to time of r cross p. Okay, using the identities between the vector identities of this form, we have derivative of r with respect to time cross p plus r cross derivative of p with respect to time. Okay, now we know that this is v cross p, because this derivative is actually the velocity of your particle. So that's plus r cross derivative of p with respect to time. Since we know that v and p are pointing in the same direction following this definition, so that means the cross product between the two is 0. Therefore, the time derivative of your angular momentum can now be reduced as this function, product r cross derivative of p with respect to time. We know that this is basically Newton's second law of motion. So this is r cross some f along the direction of r. We call this your central force. Okay? And this is what we call your torque. Okay, so this is the torque on the particle about the origin. Okay, so that means this can now be written as n equals derivative of L with respect to time. And we call this, it's commonly known as your Newton's second law of motion for rotation. As you will notice, this is very similar to the usual form of Newton's second law of motion, and that is a derivative of P with respect to time equals the net force. Okay, so we already know that. Now, okay, so following this discussion, okay, so since F is a central force, okay, that means if, for example, you have our particle here, this is the, say this is the origin, this is R, and this is your central force. Because this is your central force and this is R, and they are collinear as defined by the central force. Therefore, N, which is R cross F, is actually equal to 0. So what does it mean? It means that this implies that the derivative of your angular momentum with respect to time is equal to 0. And when you take the time derivative of something and that is equal to 0, this follows that L is constant. Okay, and this is what we call the conservation of angular momentum. So this means that when a particle is only subject to a central force, its angular momentum is conserved. So now, here we emphasize that in order for R and V, that defines in which, for example, a particle moves, let's say a planet, and this is because the angular momentum L is defined by both R and V, which is a constant in both magnitude and direction. Okay, so for example, let's say in this case, let's say this is the velocity of this particle m. Okay, because for example, if this is in x in y direction, r is in the xy plane and v is also in the xy plane, the angular momentum would be along the positive z direction. Okay, and because that direction or that quantity, that angular momentum is always pointing in the positive z direction and the magnitude is also constant because of this. Therefore, R and V will remain in X and Y plane. So if this is a planet, this particle will move in a plane. Now, in general, the motion of a particle in a central force field is really a two-dimensional problem. Okay? So, for example, we're going to constrain our particle to move in this two-dimensional coordinate system, let's say x and y. And then this is your particle m. The position vector is defined by this. And we can define this angular or angular direction theta. If, for example, this is the velocity, the velocity with respect to the position vector r will have two components. One that is perpendicular and another one is parallel. We call this component the radial component of the velocity, and we call this component the transverse component of the velocity. So it is called transverse because this component is always perpendicular to the radial direction, and of course VR is the radial direction. Okay, so because of this, we can now define the velocity vector. The velocity vector will now be equal to VRR hat plus V theta theta. And from your vector calculus, this is actually equal to R dot R hat plus R theta dot theta hat, where R hat is the radial unit vector and theta hat is the transverse unit vector. In this case, this is theta hat and this is R hat. So therefore, the magnitude of the angular momentum L, which is the magnitude of R cross MV. So because R is R hat, and we cross it with M times this one, R dot R hat plus theta dot R theta dot theta hat. Okay, this yields to this expression M R squared theta dot. And as you will notice, this is a constant. Okay, so this is the conservation of angular momentum. Okay, and so in the next video, what we're going to do is we're going to formulate or derive the equation of motion in a central force field. Okay, so I'll see you again in the next video. Thank you for watching. Bye-bye.